Hello, I'm Dave Rothery. I'm the S283 module team chairman, and I'm shooting this as an introductory video to those of you who are starting S283, that's Planetary Science and the Search for Life, in October 2019, or those of you who think you might like to start it and want to find out more about it. Okay, so it's a course that's been going in one form or another since the start of the century, but what we have in October this year is new editions of the books, which were new in October 2018, so this is the second time they've been used. So they're very up to date, very few errata in them, some annoying ones which happened when the changes made it to proofs weren't actually incorporating what we printed, but they're covered in the errata. It's minor things. So up-to-date books, very handsome books. They sell quite well in the shops as well, internationally, so it's good for our reputation. So you'll be studying from those books, but we have a module website. This is last year's website, which is what guides you through rather than printed material. And well, it happened on week 4 now, so it tells you what you'll be reading in that week and what the learning outcomes are. Let's go back, that was just a small screen. You can get the content of that chapter of the book as a PDF. Okay, let's open that. Okay, there we go. So the books are available digitally, chapter at a time, or the whole book as a single PDF if you want. So it's a course that's delivered with hard copy books, but online versions, and the assignments and the activities are all online via the module website. What does it cover? Well, it's called Planetary Science and the Search for Life, so it takes you through planetary science, which is the science of the planets and planetary bodies, moons, asteroids, comets to an extent in the solar system. And in the second book, we start to look at exoplanets, planets around other stars. There's some very exciting developments there. And the search for life bit is which ones of these are habitable? How do we find signs of life on them at the present day? And what might future technology deliver to us? And at the very end, we look at possible intelligent life elsewhere in the universe. I mean, most of the time with this astrobiology business, we're looking for places where microbes might scratch a living, and you'll find that under the surface of Mars, under the ice on Europa and Enceladus, moons of Jupiter and Saturn, are places where there could be life today, but it's most likely microbial if it's there at all. Elsewhere, with more Earth-like bodies, if that's the right place to be looking, are places where we might find more advanced forms of life, including possibly intelligence. But most of the time we're dealing with the geology of the bodies and the chemistry and physics of their atmospheres. So it's a course that's quite eclectic, quite wide-ranging, but it seems to be pretty popular with students. It's only a 30 credit module, and that's good if you don't want to be forced to study at 60 credits a year. It also means you can pair something else with it if you want to. A lot of students will pair S282, the astronomy course, which is in its final year as S282. Next year, October 2020, it will be S284, a new version of the course delivered essentially online without any books. Currently, both 283 and 282 have books. Let me show you what it's like in the books. First book, Introduction to the Solar System. Second book, Introduction to Astrobiology. So the course content, well, big list of authors who've contributed to this in the original versions and the new versions. The first chapter is a tour through the solar system. There's a picture of Pluto there. Then we look at the internal structure of the terrestrial planets, and that's what are the planets made of, the rocky planets. Other terrestrial-like bodies with iron cores and rocky mantles and possibly some ice at the surface in the case of this particular moon of Jupiter. Subduction on the Earth. Processes that go on at the surface, so we're looking at volcanism and explosive volcanism and building big volcanoes like this one on Mars. We look at cratering processes as well. So there's stuff about cratering and what the wind and flowing water does. Then we look at the atmospheres of planets, a lot of photochemistry going on, giant planet's internal structure. This is the thing that didn't have the right version of a figure in, although we changed it at proof stage. It printed the wrong blooming one, so there's an erratum for how massive Jupiter's core is. Trivial change, easy to put right. So after the giant planets, we're going to looking at orbits in general. I mean, the chapter's about minor bodies of the solar system, but this is where you learn how orbits happen. Some nice pictures of cometary nuclei and asteroids. And then we look at the origin of the solar system, and we finish off in book 1 looking at meteorites, because that's material from space that we can find in abundance on the Earth and do lots of isotopic studies on. It's quite a difficult chapter, but it's very useful stuff. Then the second book, Introduction to Astrobiology. Some of you will find this more familiar than others. It begins with stuff about, what is life, what are cells, how could life have begun, how do you get cell-like structures from polar molecules in water and so on. Then we look at what makes a planetary body habitable, what conditions do you need, what role do microbes have in changing the conditions of a planet. Earth's atmosphere didn't used to have oxygen in it. That's only there because the first microbes were munching on methane and excreting oxygen. So we built up an oxygen atmosphere which animals like us can use. So it's an interesting story there. We look at extremophiles, that's what life on the Earth means. Organisms today that live in hot or saline or dry environments, for example. Look at these things here. Cryptendoliths, green algal-like things living inside a rock in Antarctica. Then we look at Mars. One of the members of the module team, who I'll introduce you to later on in this video, is working on the rover that's going around Mars at the moment, Curiosity. There's a lot of good stuff about Mars if we're thinking of planetary habitability. We then look at icy bodies, the moons of Jupiter and Saturn in particular, as places where life might occur underneath the ice. Europa has the biggest, not the biggest, the innermost but one icy moon of Jupiter has a surface that's icy but broken into rafts. And I've got a high resolution picture on the next page, I should think. Below this rafted mass of ice, we think there's an internal ocean where life could exist, and we'll look at some evidence for that. Enceladus, a small icy moon of Jupiter, has eruption plumes today where through the ice is being vented water, which freezes to tiny ice crystals, but there's also methane and organic molecules and hydrogen. It's a good evidence that there's an ocean down there with interactions between warm rock and water, which is what you need to get you the chemical processes upon which life can piggyback. So habitability under the ice. Then we look at Titan, moon of Saturn, which has lakes of liquid methane, for heaven's sake, and river channels feeding into them. A marvellous setting to consider for possible habitability. Then we look at how exoplanets are detected. We've changed gear now. We're looking for worlds elsewhere where there might be life. So how we find exoplanets. The light of a star is dimmed when a planet passes in front of it, for example. There are other techniques, such as the star is swung to and fro by the planet going around it, so we get changes in the radial velocity of the star. Having looked at how we detect them theoretically, we look at what exoplanet systems are actually like. It's a plot of mass of planets against distance from the star. There's so many exoplanets have now been discovered. We know them in their thousands, including some around red dwarf stars. There's a TRAPPIST-1 system, and there are 7 planets known around TRAPPIST-1. Marvellous place. We didn't expect red dwarfs to have habitable worlds, but 3 of those 7 are inside the habitable zone around that star. We'll then look at how we might find life on exoplanets with spectroscopy, and then we finish off with the search for extraterrestrial intelligence. It's a wide-ranging course. Students that do it generally tend to enjoy it. I hope you'll give it a go. It is science. You do need to cope with some mathematics. Well, it helps if you cope with the mathematics. You can skip those bits and still scrape a pass on the course, well, get a moderately okay pass. But really, if you're studying on the physical sciences pathway, you should be doing okay with the mathematics. If you're coming on the geology pathway, which is a great course to include, because there's a fair bit of geology there, and for heaven's sake, if you're studying the Earth, you should study comparable planets. And the maths ought not to be beyond you. It's not that complicated, and you can sort of skip those bits if you really need to. Preparation for a course, we don't do a boot camp or anything. If you've done S111, you'll be in good shape to start this. If you want to read something, I mean, I wrote this book, A Very Short Introduction to Planets. It's Oxford University Press. It's $7.99 or something. So that's quite cheap if that would set you off. There's also A Very Short Introduction to Moons. None of that's required reading, but if you're looking for something to do, give that a go. Okay, I'm going to introduce you to other members of a module team in the rest of this video. So in here is where the modules in general get maintained. This is Lisa Mills, who's the curriculum assistant for S283. What do you do, Lisa?
Hello, I maintain the websites, I style exam papers and TMAs, and deal with day-to-day queries.
And do we give you a lot of trouble on S283?
No.
And here, carrying boxes, looking like he's really working.
I am working. I've just finished with the Royal Society Summer Science Exhibition, so these are my boxes for the lunar sample.
That's got real bits of the moon in. Yeah. And what about S283, Mahesh? What do you do?
It's an absolutely fantastic course, or a module as we call it now. It's a second level planetary science module, which everybody who is interested in planetary science must consider doing it. You learn all about planets, you all learn about how you use the samples from different planetary bodies to reveal the history of the solar system.
Now we're just getting some coffee ready for the exam meeting that we're going to be working on. But here's Susanna Spencer, who's a key member of the S283 team.
Hello everybody. Yes, I am a Martian actually, and in your materials, I looked at the Mars chapters, but I also looked at astrobiology and generally what is life out there if it is not on Earth. Of course, we haven't found any, but we keep looking. And to keep looking, we need to understand certain environments, and that's what I do in my research. I look at the rocks and the water and what happens when water meets rocks and what environments does that actually create. And those environments are what I study, and then I work with the Mars Curiosity rover, and for that we are making decisions to where to go and which of the rocks to investigate, again to understand the environment and to see what habitable environments the Curiosity rover at Gale Crater encounters. And all of this, of course, it is also going into my teaching in the course that you are studying, but also into SXP S288, which you might study after this course, which does experiments and looks into methane on Mars. I wish you all the best of luck and have fun.
No, we're just taking a break looking at the exams. Here's Manish Patel. Manish, tell us what you do on S283.
So I'm part of the course team. I contribute to the exam questions, the ongoing assessments throughout the year, and I helped write some of the text in the books that you hopefully will have read or
will be reading if you sign up to study this course.
Yeah, if there's one reason you sign up, just do it so you can read the bits I wrote in Introduction to Astrobiology and the Solar System. The Titan chapter in particular, I can recommend. It's a very good read.
Okay. Now, you're not working on Titan at the moment, research-wise. What are you doing? Because this is exciting.
Indeed. I started my career on Titan, way out there in the solar system, and I've moved back closer to home as I've carried on. So now I'm orbiting Mars. So I've got an instrument orbiting Mars at the moment, which is looking at the atmosphere of Mars, looking for interesting gases like methane that may link to life or may not be there even. So we're going around the planet constantly all the time, getting data all the time, trying to find these interesting gases.
Yeah, I mean, we do have news on the S283 module website, news items cropping up. So look out during the year for news of methane detections on Mars. It's been detected by the Curiosity rovers system, but it's harder to find in orbit.
It's a very interesting debate on what's happening, how to couple what you see on the ground to what you see from space. So this is a whole nother debate going on in the Mars science community. So keep your eyes peeled. and ask questions away when you start hearing about the news.
Well, that's about it. I'm recording this bit now after we've had our exam meeting. We're very pleased with how it worked this year, but I thought I should just say a little bit about how the exam works. There is an exam at the end of this module, unlike some other modules these days. It's designed to test not so much your memory as your understanding. We expect you to know how far it is to Jupiter. Jupiter's 5 times as far from the Sun as the Earth is, and Neptune, for example, is 30 times further. Basic facts, but very few formulae are required to be remembered, and most information that you need will be given to you. We want to see what use you can make of that information. So do the TMAs during the course of the year. You have to get 40% overall to be allowed into the exam. And then in the exam, there are 3 parts. First part is computer marked, 8 multiple choice questions. Then part 2 and part 3, basically are one book each. And there were 36% of the marks each. So the computer marked questions, 8 of them. I mean, last year, the current year now, last year for you, this is how far is Jupiter from the Sun, and now how heavy is it? If you can't pick the right answers off that list, you've not really learned very much about the solar system. This is a figure in question 2 that you've met in one of the course books, and it's basically wanting you to identify which of these internal cross sections represents the planet Mercury and some facts about it. There's a question here about this elongated impact structure. There's a question here about orbits. There's a question here about the chirality, that's whether molecules have mirror images of each other or not, which is relevant to life. Question about habitability and extremophiles, that's organisms living in extreme environments. This is what did we find out about Titan by the Cassini probe, and this is about exoplanets, frequency or how often they're found versus size. And this is a figure that you've met in the module, so you should be able to recognise what it's telling you. Then parts 2 and 3 have 4 questions each, and you've got a choice. You only answer 3 questions from each part. This year, the first question was about Io and Europa. Second question was a fairly standard question. It was plotting some data up, meteorite composition, and this is a very standard question that most students will choose to do each year on this diagram here. So you'll meet spidergrams, as they're called, quite early in book 1. It's a very powerful way of understanding compositions and how things have evolved. Question 11 this year was about stages in the formation of the solar system. Question 12 was saying here's a spectrum of 3 different meteorites, and what type of, what does it ask you for? Which of these is a C-type meteorite? So this is a figure you've seen in the block, and the rest of the question is asking you about asteroids. We've been through 4 questions there. I have in part 3, there's 4 more questions. First one this year was about the use of carbon isotopes for fingerprinting biotic processes, basically, and a little bit about amino acids. Very long-looking question, but very short parts. Scored quite well. Here's a question we hadn't tried before. It shows you a digital terrain model of Mars. It's a sort of map view version of what's on the cover of this second book, asking you to use this to deduce features about Mars's history. And that was very well answered, actually. There was a question about exoplanets going in front of their stars. Again, these figures have been seen in the book. And the final question was about attempts to communicate between civilizations on different stars, Bracewell probes and von Neumann probes, and then the famous Fermi paradox, which is, if the universe is teeming with life, or if the galaxy is teeming with life, why can't we see signs of it? So your paper next July will be very much like this one, on exactly the same questions, of course, but the same style, covering the same range of subjects. Do take a look at the specimen exam paper that's provided online via the module website to give yourself some familiarity with what's coming and how to fill in one of these computer marked forms which you may have not met before for computer mark part of the exam. And there are exam revision tutorials offered at the end. So make good use of those when you get to the end of the year. Please join in the forum. Please talk to me and the fellow members of the course team. Please talk to your tutor and your fellow students. Have a great year and enjoy it. And I hope to be making your acquaintance in October when the course begins. Bye.